Welcome back to the Deep Dive. Today, we're talking about a crisis well, it's happening in slow motion. It's not, a big cinematic asteroid hitting the planet or a sudden viral outbreak. It's much, much quieter.
But maybe more dangerous. We're talking about the silent pandemic. And no, that isn't a term we just made up.
Right.
That's the scientific term for the crumbling foundation of modern medicine, antimicrobial resistance.
AMR.
Basically, the drugs are starting to fail. The germs have outsmarted us. But today, we're not just listing problems.
No.
We're going to do a really rigorous line-by-line look at a solution that's just been proposed. It's from a brand new perspective paper published just a couple weeks ago, January 3rd, 2026, in Nature Communications.
The paper's called From the Lens of Early Career Researchers, and it's from the Futures AMR Network. The authors, Nikhil Bala, Linda Oyama, and others, they're essentially arguing that biology alone can't fix this.
So what's the alternative?
They're proposing a radical new way to fight disease, led by what they call the New Guard Early Career Researchers, or ECRs. And we're going to break down their specific ideas. I mean, we'll get into how they're using things like musical theater to change how we use drugs.
And technology that can literally hear bacteria.
Yeah, that's the sci-fi part that got me. But before all that, you have to set the stage. The paper mentions a brain drain. Why are people leaving this field if the problem's getting worse?
Well, that's the paradox, isn't it? You'd think it would be a boom industry. But the source points to this valley of death in R&D careers. The funding is just so uncertain.
So it's a job security issue.
It is. You have brilliant people spending half their time just writing grant proposals that probably won't get funded, so they leave. We're losing the experts right when the superbugs are winning.
Okay, so the paper's mission is to stop that bleeding, to empower this new generation. Let's get into their first big idea, the societal puzzle. They say AMR isn't just a medical problem, it's a relationship problem.
Exactly. And let's zoom in on that because it's so important. If you only see AMR as, strong germs, you're missing the whole picture.
You miss the cause.
You miss the cause. The source argues that the rhythm of this whole biological dance is really set by us, by human society. And they give a really detailed case study on low and middle income countries, LMICs.
Right. Let's unpack that. They list these specific cultural barriers. The first one is this idea of strong medicine.
Yeah, this is a fascinating one. In many communities, there's a cultural belief that antibiotics are a kind of cure-all.
Silver bullet.
The silver bullet. Got a cold, which is a virus. Feeling tired, you want the strong stuff. The antibiotic does absolutely nothing, but the demand is there, and it forces doctors' hands.
Which connects to their next point, right? The economic pressure on what they call informal providers.
It does. I mean, imagine you're a local pharmacist in a small village. A family comes in, they've scraped together what little money they have. If you tell them, oh, it's just a virus, go home and rest.
They feel cheated.
They feel cheated. They think you're holding back the strong medicine. So to keep your customers, to keep your business afloat, you sell them the antibiotic. It's a business decision that fuels a global health disaster.
And then there's the household stockpile.
The just-in-case stash. We all know someone who does this.
Yeah.
You feel better after a few days, you stop taking the pills, and you save the rest. Then a few months later, you get sick and take a couple of the leftover pills.
As half dose.
A half dose. It's the perfect recipe for creating resistance. You're exposing the bacteria to the drug, but not enough to kill them. You're training them, making them stronger.
So the big takeaway here is that you can invent the most amazing drug in a lab in Boston, but if a sociologist hasn't figured out why a family in a village is saving leftover pills, that drug is basically doomed from the start.
It is. Resistance will emerge before the drug even turns a profit.
Which brings us to the second, and I'll be honest, the most surprising part of their solution. We have the social scientists. Now, they argue we need artists.
The arts as an ally. And look, this isn't just about making pretty posters. This is about cognition, how our brains actually process information.
What do you mean?
The data on AMR is abstract, things like log reductions or minimum inhibitory concentrations. For most people, that's just noise. It goes in one ear and out the other.
Right, it doesn't mean anything.
Exactly. So the paper says we need to turn that noise into a clear signal. And they give some amazing examples like the graphic novel approach.
I love this idea. They talk about turning a hospital ward into a literal battlefield.
Yes. Instead of a boring chart with infection rates, you see doctors in armor fighting these huge, monstrous superbugs. It uses a visual metaphor to make an invisible threat feel real and physical and dangerous.
It hits you emotionally, not just logically.
That's the key. And then there's the musical they mentioned, Lifeline.
Tell us about that.
It's a brilliant piece of storytelling. It runs two timelines at once. In one, you have Alexander Fleming, back in 1928, discovering penicillin, this moment of incredible hope. And in parallel, you have a modern-day doctor trying to save her partner who's dying of sepsis because none of the antibiotics work anymore.
Wow. That's a powerful contrast.
It creates what they call emotional engagement. The audience leaves the theater actually feeling the loss of these medicines in a way a government pamphlet could never achieve.
And for a simple memory aid, let's talk about the monster hand.
This one's for kids. It's so clever. It's a hand-washing station for schools, but it's shaped like a big, friendly monster. To wash your hands, you have to literally scrub the cartoon germs off the monster.
It gamifies hygiene.
It does, and the paper says this stuff actually works. They cite the Antibiotic Guardian campaign in the UK, which showed that these creative approaches lead to real, self-reported changes in behavior.
People finish their prescriptions. They wash their hands.
Because they remember the story, not the statistic.
Okay, we're about 5 minutes in. Let's do a quick recap of this first part before we get into the tech.
Sounds good. So the soft science strategy is this.
First, the problem isn't just biological. AMR is driven by our behaviors, like stockpiling pills or the myth of strong medicine.
Right. And second, the mechanism is often social or economic pressure, like pharmacists having to overprescribe to stay in business.
And third, the solution is to use the arts graphic novels, theater, even fun designs, to turn that abstract data into an emotional story that actually changes how people act.
So your bullet point takeaway is, science might discover the cure.
But art and social science make sure we actually use it right.
Precisely.
Okay, let's pivot, because this is a Nature Communications paper, so we have to talk hard science. The paper goes into detail about how these early career researchers are changing the lab itself.
And this is where their advantage as digital natives really comes into play. They're bringing AI, advanced physics, into the world of biology. Let's start with how they're seeing things. Cryo-EM.
Cryo-electron microscopy. Can you break that down for us?
Sure. So imagine you want to take a really, really detailed picture of a tiny protein on a bacteria. Normally, if you freeze it, the water inside forms sharp ice crystals.
And that would destroy it.
It would shred the very structure you're trying to see. You'd get a blurry mess. But cryo-EM, it freezes the sample in liquid ethane so incredibly fast, we're talking milliseconds, that the water doesn't have time to crystallize.
Wow. So what does it become?
It becomes like glass, a state called vitreous ice. It's like freezing the protein in time, perfectly preserved.
And that lets us see its atomic structure.
Exactly. We can see the actual lock-and-key mechanism. We can see how a drug fits, or more importantly, how a resistant bacterium has changed its lock so the key doesn't work anymore.
So once we can see the target, we need better weapons.
Yeah.
The source mentions bacteriophages.
Phages. These are viruses that have evolved for millions of years to do one thing: hunt and kill bacteria.
The enemy of my enemy is my friend.
Pretty much. It's an old idea, but ECRs are using modern gene editing to basically create super soldier phages targeted at specific superbugs.
And then there's halicin. I love the story behind this one.
Named after HAL 9000 from 2001, a space odyssey, and for good reason. Halicin is an antibiotic that wasn't found by a person in a lab coat mixing chemicals.
It was found by an AI.
A deep learning AI, yeah. It analyzed thousands and thousands of chemical structures and predicted which one would kill bacteria in a way that human scientists had just completely overlooked.
That's the digital native advantage. But the tech in this paper that really, truly blew my mind was the sensors. The whole idea that we need to find these bugs faster.
Speed is everything. With sepsis, for example, every hour you wait for the right antibiotic, the risk of death goes up by about 8%. Waiting 2 days for a lab culture is a death sentence.
So ECRs are developing biosensors. Explain SPR first.
Surface plasmon resonance. Okay, picture a tiny gold-plated sensor. You coat its surface with a molecule that acts like Velcro for one specific type of bacteria. When you shine a light on it, the light reflects in a very specific way. But when the bacteria land and stick to that Velcro, It changes the mass on the surface, and that changes how the light reflects.
It's instant.
It's instant. The reflection shifts, and an alarm goes off. You know the bug is there.
But that's not even the wildest one.
Yeah.
Let's talk about the acoustic sensors.
Yes, this is where we get to listen to the bacteria.
How is that physically possible? I can't hear a germ.
You can't, but a special material can. The sensor is made of a piezoelectric material. All you need to know is that it's a crystal that vibrates at a super stable, super precise frequency when you pass electricity through it.
Okay, like a perfectly tuned guitar string, just humming away.
That is the perfect analogy. Now, what happens if you stick a tiny piece of gum on that vibrating string?
It gets heavier, the vibration slows down, the pitch drops.
Exactly. That's what happens here. When a single bacterium lands on the sensor, its tiny, tiny mass is just enough to change the resonant frequency of that crystal.
So the sensor is detecting the thud of the bacteria hitting it.
In essence, yes. The frequency shift is the sound of the bacteria. And the best part is you feed that data into an AI, and it can learn to tell the difference between the sound of E. coli landing versus the sound of staph.
That's just unbelievable. And the goal is to make these cheap enough to be disposable.
Disposable, portable, for a field clinic in a remote area, no lab, no waiting, just listen to the sample.
So who are these people inventing this stuff? We keep saying ECRs, but the paper actually gives a really strict definition.
Yeah, it's important to know who this new guard is. An early career researcher is someone within 8 years of getting their PhD, or within 6 years of their first academic job.
So they're relatively new to the scene.
They are. And Table 1 in the paper, it's great. It analyzes their specific advantages, their superpowers, you could say.
Let's go through them. First up is agility.
Agility is about taking risks. A senior professor with a 30-year career, a big lab, they often have to stick to safe science to keep the grants coming. They have a lot to lose.
But an ECR?
An ECR is hungry. They are willing to bet their career on a wild, high-risk, high-reward idea, like an acoustic sensor.
Okay. Second is transdisciplinary.
This is huge. They don't see these rigid walls between fields. To an ECR, mixing art, sociology, coding, and biology. It's just normal. They haven't been told for 20 years to stay in their lane.
And the third one is digital natives.
They grew up with this stuff. AI and big data aren't some scary new thing. They're just tools in the toolbox, like a pipette or a microscope.
Now, the paper is careful to say they shouldn't just replace the old guard, right?
No, not at all. It's about a complementary relationship. The senior investigators have the institutional wisdom, the political know-how. The ECRs bring the disruptive innovation. They need each other.
Okay, let's pause for our second recap. We've covered the tech and the people behind it.
All right, here's the summary.
The tech is shifting from old-school Petri dishes to things like piezoelectric sensors that listen for bacteria, and using AI to discover new drugs.
And the agents driving this are the ECRs, these digital natives who are within about 8 years of their PhD.
And their core strategy relies on that high-risk, high-reward agility that older, more established science sometimes struggled with.
Exactly.
Which brings up a question for you, the listener. If you had a little handheld device that just hummed quietly whenever you had harmful bacteria on your skin, would you become obsessed with washing your hands?
I think I would. It would make that invisible world impossible to ignore.
But that brings us to the big problem. If we have this amazing tech and these brilliant people, why are we still losing the war on AMR? The paper calls it the Valley of Death.
This is the absolute crux of the problem. Table 2 in the paper breaks it down. The Valley of Death is the giant gap between a cool idea in a university lab and an actual product on a pharmacy shelf.
So what's the mechanism there? Why does that gap exist?
Okay, so our ECR invents that amazing acoustic sensor. It works. They publish a paper in Nature. Success.
Right. Sounds like it.
No, because to get that from a single prototype to being manufactured by the millions, that takes industrial scale-up, clinical trials, marketing. That takes tens of millions of dollars.
And academic grants don't cover that.
Not even close. And big pharma companies are hesitant because, frankly, a new antibiotic doesn't make as much money as a new cholesterol drug you take for life. So the invention it falls into the valley and it dies.
Creating that brain drain we talked about.
Exactly. The researchers get burned out and leave.
The paper also mentions regulatory opacity. That's the red tape.
It's the red tape. If you invent, say, a new diagnostic tool based on CRISPR, the FDA or the European regulators might just look at it and say, we don't have a box for this. Is it a drug, a device? That uncertainty can add years and millions of dollars in delays.
And then there's the data problem. Data silos.
Oh, this is a massive inefficiency. You've got genomic data on one server, patient data in a hospital's records, social survey data somewhere else.
And they don't talk to each other.
They don't talk to each other. They're in different formats. It's a mess. So the sociologists studying prescription habits can't easily connect their findings to the biologist who's sequencing the resistant germs from that same region.
And the ECRs are pushing for a solution called FAIR.
Right. FAIR.
Let's spell it out.
It stands for findable, accessible, interoperable, and reusable. The key word there is interoperable.
Meaning they can talk to each other.
Yes. Like having a universal translator for all scientific data, ECRs are pushing for these open standards so we can combine all this global data into one giant intelligent weapon against AMR.
And the source touches on one last challenge, a very specific ethical one: parachute science.
Yeah. This is a term for a really bad habit that, Western science has had for a long time. Researchers fly into a lower-income country, they take samples, blood, water, whatever, and then they fly home to their fancy lab, publish a paper, and get all the credit.
And the local community gets nothing.
Right. And it's not just an ethical failure, it's a scientific one. Because if you design a sensor that needs a stable electrical grid to charge, but you never ask the local nurses if they even have reliable electricity, your solution is useless.
So the paper argues for co-design.
Building the solution with the people who will actually be using it. It builds trust and it makes sure the tech works in the real world, not just in a lab.
So how do we fix all this? We're in the final section now, the path forward. What does this new guard actually want?
They want power in the system. First, something they call reciprocal mentorship.
So a two-way street.
Exactly. The senior professor mentors the ECR on how to navigate university politics, but the ECR mentors the professor on how to use AI or new digital tools. Both sides have value, both sides learn.
And they want a literal seat at the table.
A seat at the table. They need to be on the advisory boards, the funding panels, the groups that decide strategy. Too often those boards are filled with people who haven't been on a lab bench in 20 years. You need the people doing the work to help make the decisions.
And the source lists some of the actual networks that are driving this.
It does. They mention the Futures AMR Network, or FAN, who wrote this paper. Also, ChemoNet and the Fleming Initiative. These are the organizations where this new generation is getting organized.
With the ultimate goal of One Health.
One Health, which is the final piece of the puzzle. It's the understanding that you can't fix human health in a vacuum. Animal health, environmental health. It's all one interconnected system.
The antibiotics in farm animal feed end up in the water supply.
And that ends up driving resistance in humans. It's one system. The paper has a great diagram, figure 1, that shows it as a puzzle. You need all the pieces, science, tech, arts, policy, society, to fit together at the same time.
And the paper ends by saying that the ECRs are the ones holding those pieces because they're the generation that will have to live through the worst of this pandemic.
They call it microbial stewardship.
I like that term.
It's a great term. It changes the mindset from a war on germs, which we can't win, to management. How do we live with microbes safely and sustainably?
Okay, let's wrap this all up. We've gone from the sociology of a village pharmacy all the way to the vibrations of a tiny piezoelectric sensor. We've looked at the brain drain and the valley of death.
And we've seen the argument that the solution requires a totally new kind of scientist, one who's part artist, part data analyst, part biologist.
So I want to leave you, our listener, with a final thought to chew on. We talked about two very different weapons today. There's the acoustic sensor, the hard tech that can literally hear a single bacteria land.
And then there's the graphic novel, the pure storytelling that makes a hospital ward feel like a battlefield.
Exactly. So here's the question. In the fight against the silent pandemic, which of those two is actually more critical for the public? Is it the technology that can detect the bug? Or is it the story that convinces a person to actually care enough to finish their pills?
That really is the question, isn't it? Can the best hardware in the world save us if our cultural software doesn't get an update?
We'll let you decide. This deep dive was based on the Nature Communications Perspective paper from January 2026 by the Futures AMR Network. And if you get a chance, go look up the monster hand design. It's brilliant.
Keep questioning. Keep learning.
And we'll see you in the next deep dive.